So I have to preface this question by noting that I'm not up on the details of how our current regulatory agencies operate, but you often read folks lamenting that regulatory agencies aren't doing enough to look at nanomaterials as different from bulk materials of the same substances. And from what I understand, folks like the FDA and the EPA are looking at various nanoparticles on a case-by-case basis, looking at cases where there may be sufficient reason for concern to look at them much more carefully. And I was just curious for you folks what you think of that case-by-case approach, and if you were giving these regulatory agencies advice, how you would suggest that they operate in terms of trying to pick the cases that deserve extra scrutiny. And you also hear worries that perhaps there are just so many factors that can vary with nanoparticles you can't come up with easy generalizations, at least in the near future, as to what deserves extra scrutiny. So I was just curious what your thoughts would be for the regulatory agencies approaching these issues.
Yeah, with respect to, as you just said it, I mean, because there are so many differences and the outcomes can be so different, I think at the moment we really have to collect more data. And I'm sorry to say that we need more research, what was mentioned before, but we really need to have more data to be able to come up with a more uniform assessment and maybe be able to classify then certain classes of nanomaterials. Some talk about QSAR, but I'm not sure that this will ever work. And then being at a better, in a better situation to predict what might be happening, but we are not there yet.
Well, I have an answer because, I mean, I look at it and what's out there in the greatest quantity and what's the most of the population going to be exposed to. And I look at TiO2 as, from my point of view, that's what I see. Now, maybe there are others and you all can comment on it, but, you know, you start with things where, you know, if you look at this model for risk as being hazard and exposure, TiO2 you're being exposed to. I mean, carbon nanotubes, maybe at some point you will be, and others the same thing, but here's where it's already part of the general population. Where should we be worrying about this?
Yeah, I'm not sure. No. Sorry, may I just... Go ahead. With TI2, I would not really be that much concerned. Would that something you would be concerned with? TI2?
Well, I'm just pointing out, I mean, whether I am not have a personal concern, but if there is a general population concern over nanomaterials, that's the one they're exposed to. And so if there's no concern, great, then we ought to be able to do the studies to point out that you should have no concern, but that's the one I would focus on.
Yeah, and again, I mean, with TI2, I would not have any concern, but I would also at the same time be careful and not leading the public into believing we should not be concerned at all. But it would not be one material that it clearly has been investigated quite a bit. There are long-term inhalation studies. In fact, you can argue that in the early long-term inhalation studies, the nano-TiO2 caused lung cancer in rats at these extremely high levels here for 2 years being exposed, which I think the scientific community agrees that this is very specific for the rat model as being a so-called overload effect. And this new study I showed with TiO2 in the feeding study, I certainly would like to see that confirmed also with respect to finding out if indeed these TiO2 particles at these high doses got into the target tissue like the bone marrow.
Yeah. Charles? Yeah, it's a quick, trying to decide which of my 82 questions I want to ask here, but great connection on the talks here. Maybe this plays into what should the regulatory agencies have their eye on, because there will be more nanomaterials being introduced into the marketplace. Of the many hundreds, if not thousands, of measurements my field team has made over the last 3 years, one question always comes up, and that is how representative of what we're seeing in the toxicology studies is what we are seeing in our field samples that we collect. Because I can tell you that 99 point whatever percent of the samples that we see of an airborne aerosol are agglomerates of these materials. And how do we factor that into our overall risk assessment? How do we evaluate that from an overall exposure standpoint? And how does that factor into what we're doing on the toxicology? And maybe this is a long-term 2-day discussion, but I know it's a very real scenario that we do a lot of study and a lot of work on the primary particle. We know they agglomerate, and that's what we see out in the environment and in the workplace. And so how are we factoring that into our predictive and our actual toxicology models?
Yeah, I mean, here the question is, again, the studies that we and others have been have been doing with TiO2, nano-sized PiO2. These were all agglomerates, not individual single particles in the airborne state. It's different from when you instill it or so. And the amazing thing is, Pratim showed this old study of ours where we compared anatase large particle TiO2 with the P25 TiO2, and these were agglomerates, but still it was amazing that the dosimetric surface area correlated quite nicely. So the surface area was again the unifying dosimetric. And other studies of ours, we compared carbon black and TiO2, and that was an installation study. Again, they were agglomerated for sure, but there we saw that apparently, and we don't know much about it, apparently in the lung there can occur some de-agglomeration. For example, with the TiO2, we found more in the interstitium in lymph node as opposed to carbon black.
Yeah, my take is I think you have to do both kinds of tests. The pure pristine material gives you fundamental scientific information, and then you see how it acts in a matrix. I think that's what you're trying to allude to. But I don't know if there are some quick assays. Can I take a toxicological test to the workplace? I'm not an expert on those tests. Of course, Gunther might know, but maybe we need some representative, localized testing.
I just wanted to return back to Kevin's question and speak to the FDA's regulatory schema. And I would say that in overview, the FDA deals with products that it regulates in terms of the statutory definition of the product, going from food on the one hand, which does not require pre-market review, pre-market approval, to medical devices and drugs and biologics, which do require pre-market approval. And so the FDA would first look at what category of product is this, and then decide how closely to look at it in terms of pre-market approval or not. And the other thing that the FDA has stated repeatedly is we do not regulate technologies, we regulate products. And then again, using this pre-market or not approach or post-market approach. And the FDA, we'll hear more about this tomorrow because we have an official from the FDA speaking, of course. We'll hear more about TiO2 because there's a whole paper just on sunscreens. But I think another thing to keep in mind is that the FDA did become concerned about nanoparticles in products, especially in products that did not go through the pre-approval process. Obviously, it was looking at all new drugs, all medical devices, so as I said yesterday, that was less important. But at the time the FDA started having public stakeholder meetings, which I believe is around 2005, and 2006, there were already, according to the Woodrow Wilson Penn studies, there were already hundreds of consumer products on the market with nanoparticles in them. And we'll talk more about this tomorrow. Nanoparticles do not need to be declared on the label under current FDA law, so it's another issue. We don't even know how many FDA-regulated products are in the marketplace. But I would say that for the products that do require pre-market approval, including new food additives and new color additives, which are used in cosmetics, then that is on a case-by-case basis. So, but we would start with the statutory definition. One other comment that relates to TiO2 that has come up over and over again is that the consumer group called Consumers Union, the same group that brings us consumer reports that we read to figure out what car to buy or what refrigerator to buy, petitioned the FDA, I believe in the form of a citizen's petition, which is also covered by regulation, in 2008, and said to the FDA, we hereby petition you to look at TiO2 in sunscreens and also in cosmetics, and please give us your official position as to the safety and use and regulation. And to my knowledge, the FDA has not responded yet, but maybe we'll learn tomorrow morning.
Two mundane questions. Is anybody in the room aware of a list of all the different structures that are with the top 100 nanomaterials. For instance, the phases, the forms, the gentleman in the middle had these different flame structures. I have looked, I mean, I read MSDSs all the time, and I have not found one place that has all of these allomorphs listed in one place. That would be, it's real basic data, but I can't find it. That's the first question. The second question is there a resource that, along with the allomorph question, that essentially gives an overview of these materials that are the metals, which metals are targeted, why they're targeted for use, what's the theory of choosing the different elements? Is there a list of those? These are two basic things that I just can't find.
On the first question, there is, if you think of crystal structured databases, there are crystal structured databases, if that's the kind of thing you're looking for. NIST has one in particular. I can show you later.
Okay.
So, and I think that's what you're asking. You want the various crystal modifications on these things, and it's an inorganic database. But there are other databases as well that likely have this, but it's not all. It's clearly not all in one place. Then, if that's what you're looking for.
No, well, when you read MSDSs, it'll list off all the ingredients, but then, interestingly, if anybody didn't know this, if there's less than 1% ingredient in the process at hand, it doesn't have to be listed on the MSDS. And so there are these processes. No, not for industries. I'd like a list in one place where everybody's playing with, I'm playing with nanotubes, with cerium, whatever. And to say, oh, these are the targets, whether they're metals, they're carbon structures, and if anybody has like a philosophical reason as to why the scientists or the industrial engineers chose these different materials. So like I choose this because it's a catalyst. I chose this because of those logical underpinnings of why you chose the different atoms in allomorph. You're right, I know, but...
So with crystal phases he alluded to, and if you look up any X-ray diffraction instrument manufacturer, there is a database, JSPS, I think, which gives all the standard crystal phases for a given compound. So I think someone mentioned the need for a curated database, and I think we really need to do that in this field. Maybe one of the federal agencies. I don't see some. Now, HHS, I think it's Health and Human Services, has a very nice database, so you can go and type in titanium dioxide. It'll give you the 600 products in which TiO2 is used, and what levels, what crystal phase. I found that to be one of the better databases. Actually, someone here pointed that out to me, and there are some here and there, but I don't know if that answers your question.
Very specific to the use of an engineered nanomaterial for commercialization, product improvement, whatever it might be, that database doesn't exist. NIOSH took a run at it about 5 years ago by creating something called the Nanoparticle Information Library, feeling that researchers would gladly volunteer their information about the morphology, the structure, the synthesis, the characteristics of their particles. We very quickly learned that this was very fast-moving and a very proprietary market full of proprietary intellectual property, confidential business information. Those were all the reasons why we were told the database was never populated. We're taking a different try with it now. We spun it off, and it now has a new home at Oregon State University in that nanoscience consortium up there. It's still called the Nanoparticle Information Library. But the intent there was an open, an open database for people to share information. It's not very comprehensive. It's starting to rebuild again. So I think you do have to search in a number of places, such as the ones that were just mentioned. I think Pratim mentioned the HHS database. I don't know if that's the one that National Library of Medicine maintains or the HSDB, the Hazardous Substances Database. But there are some, if you punch in any chemical name, you'll get more information that you want. The question is it the nanomaterial form information that you want?
What's the compulsory statutory or legal mechanism for disclosing these things in products? I mean, usually I use the TSCA when I have to compel a manufacturer if they're exposed, if I have a worker that's exposed to a material. But I'm not aware of any statutory or other mechanism that essentially says to a manufacturer, what is in this material? What is in this product? List everything, everything, absolutely everything. I am not aware of that mechanism.
There isn't one.
Thank you, okay.
But it's evolving. There's very good moves being made in Europe with the globally harmonized system of chemical hazard classification and labeling. Some of that will be adopted just because we have so many international companies that deal with or are based here in the U.S. There's also a growing recognition as some very healthy product stewardship and responsible activities with major companies who will disclose additional information on their material safety data sheets. But there's still many folks who will retreat back to the original requirement of a certain percentage and meeting the definition of it being a hazardous material. So there's still some trading pieces.
Can I make one more comment on databases, because I'm running into the same issue. I'm very interested in data with ceramic materials, and you see the same issue. It's probably not as difficult. But one thought has always been, could we construct a database of databases, and at least you know which ones, you heard a few mentioned today that, give somebody where to go look. Maybe there'll never be one comprehensive one, but for individual property issues and so forth.
Isn't that one of NIST's new initiative under some of the new...
I don't know the specifics of whether that's an intention. Yeah.
It would be a hub or a database of data.
Yes. But I don't know whether, I really don't know what their exact program would be there.
In this context, I want to ask the panel to address a problem question. If nanoparticles or if nanomaterials are less than 1% of a product, then it doesn't have to be listed in the MSDS sheet, for example. And so I want to pick up on a point that Pratim made in his talk, where we should probably try to learn from the mistakes of the chemical industry and ask questions about low dose, long-term exposure. And so I wonder, Gunther, is it a reasonable thing to use, for example, to use accelerated testing schemes? If you're testing a transistor for reliability and you want to know if it's going to last for 10 years, what you do is you heat it up and you test it very aggressively. So I'm wondering if I could do the same thing with, for example, cells, where I electroporate the cells, open them up, and to allow the penetration of nanoparticles into the cells and see how messed up they get in a short time. Is there an accelerated testing scheme besides high dose?
No, I don't think that there is what you just mentioned, to open up a cell pores, for example, or make it more diffusive. That's not what's happening in vivo. In a long-term, low-level exposure, what is going to happen is adaptation occurs, and organisms, tissues adapt, build up defense mechanism. If you, to begin with, destroy that, then the cell has no time to really adequately mount these defense mechanisms. In fact, what you do, you force the particles inside. It may be, and that again is something to be looked at, it may be you are trying to simulate a susceptible organism, a susceptible tissue.
Actually, what I'm looking for is to eliminate this partition. You know that the cell membrane is going to be very good at excluding most of the nanoparticles. So I want to get rid of this high dose scheme and go to low doses, but get the nanoparticle, simulate the situation where the nanoparticle, where we've had long-term low dose exposure of a cell by electroporating the cell and then pushing these particles in, and then seeing how proteins agglomerate and accelerate the testing. So, of course, transistors don't usually see 150 degrees Celsius and 10 volts as opposed to 2 volts, but we expose them to those kinds of conditions in order to test reliability in 3 days, reliability that we would see over 10 years. And so that's what I'm wondering, if there's some way of accelerating the testing.
Well, transistors also are not living organisms. They cannot mount a defense. Yeah. So if you expose them, sure, that's quite a bit different. So I don't know. I mean, if you can prove that indeed what you're doing was electroporating or whatever you might be doing, that this is equivalent to a long dose exposure and a chronic response, that would be fine. But I doubt it that you will be able to do that.
A comment and then a question. The comment on the data issue. My understanding is that the current reauthorization of the America Competes Act that's that's going to happen in Congress contains a provision authorizing the National Science Foundation to compel some formal archiving and release of data, and that might in fact be an instrument for this kind of collection for academic researchers, given that NSF funds a quarter to a third of NNI-sponsored research. So that might be a way to get at the catalog of materials at the research and laboratory level that could help constitute part of what's missing. The question is, I'm glad this slide is still up because it's really such a profound and detailed description of at least a certain portion of what the risk paradigm is. And, I'm wondering, given, going back to the very first lecture from Professor Lieberman that we had about the array of nanomaterials that we might have to pay attention to, and looking backward through some of the regulatory processes that are going to involve this aspect of risk assessment. So, we've got this process up here that needs to be multiplied for not just every sort of category of nanomaterial, but potentially every species underneath a genus of nanomaterial. And then when the regulatory process is going to look back at it, it's going to look and see whether, in fact, it occurred through any standardized processes that might or might not have been adapted at the time. It's going to look only at, of course, that segment of the literature that's ended up being peer-reviewed. Within any particular peer-reviewed piece, there are going to be questions about how rigorous that piece was, how standardized it was, how consistent it was with other competing protocols that we have seen from the literature already. There are different sets of findings, and when you add this all up, what kind of timeline? Again, thinking about the 80,000 chemicals backlogged at EPA, when you add this up, what kind of information for regulatory decision-making on what kind of timeline is the risk paradigm actually going to give us when, all the predictions for nanomaterials in commerce are, sort of going through the roof? And is it, in fact, the case that the risk assessment paradigm is sufficient to handle that challenge?
I think, in my view, it would be nice, and it should be a goal, to develop validated and verified high-throughput assays where you can really do a number of hundreds of nanomaterials in a very short time, but they have to be validated. And I think it would as well be very nice to be able to then define a hazard first of all. I pointed out this hazard scale, and that's one way. There may be other ways. So at least to get some information about a hazard of a nanomaterial. And for that, to do that in a high-throughput assay, that would already be very, very helpful. If you then, in addition, if you want to get to the risk assessment paradigm, if you then have at least some predictions of what human exposures might be like, then you could at least attempt to do such thing. But without that, and high-throughput assays are being done now, and I have not seen that they have been verified and validated in vivo tests. And if after a year you have lots of materials in and you have done high-throughput testing, it turns out, well, that was not really very valid what you did there, and it's all for nothing, yeah? And take an example, zinc oxide particles. They are in a vitro system, are very reactive, very inflammatory, induce oxidative stress responses. Zinc is an essential element. We need that. And so I would, and the reason why they are so active in an in vitro test, also in acute in vivo test, is because it's solubilized very quickly. The retention half-time in the lung is only 6 hours, so it's dissolved after 6 hours, and it's gone then. So I would not be that terribly concerned about zinc oxide showing in vitro test a high acute inflammatory response.
One more point, and then we're out.
I have a question, deliberately very much of an outsider's question, a spectator, as maybe a science policymaker who looks at nanotechnology and has listened now to these talks. And especially the first two talks paint a very, very different picture in some sense of what nanotechnology and nanotechnology research is. And so people might need help to have this reconciled. I mean, the first picture is one where we say, after all these years of nanotechnological research, there are all these very basic measurement needs still. And so, some people might say, how can this be? I mean, there's all this nano research going on. People don't even know how to do these rather basic kind of measurements and so forth. And so there must be obviously a way of doing nanotechnology research where it's perhaps not needed to know so well or so exactly what you're doing. And then in the gas phase kind of example that you were presenting, there was a certain ideal of what it means to understand every step of the way of what a process is, and that step of the way includes knowing in some sense very, very precisely and being able to measure also very precisely what's going on. So these are like two different kinds of nanotechnology research almost. And how do they come together? And especially, again, why is it even possible? I mean, how do we explain to people that it's even possible to have all these results and still say that all these measurement needs are unmet?
My presentation, you have to take into context these are measurement needs for developing environmental health and safety criteria. So it's not to manufacture nanoparticles or to figure out how they're used. So it's really in the EHS context. And remember the hundreds of nanoparticles you heard all through this workshop, how many different kinds of nanoparticles. So yes, some of them have been measured. But measurement on that kind of small scale is quite difficult. And so it is not obvious how you measure all of these. And you take a carbon nanotube and they differ. You might have 20 different kinds of carbon nanotubes. And what is it you want to measure about it? It's not trivial. So there's a lot of work going on, but there's a lot of work to be done. I think most of what I put up there is true. Those measurement needs still exist. People can say, no, we know how to do all of that. That would be great. But I think it's the extent of the field particularly and the size of what we're trying to measure. It does extend our technology, our measurement technology quite a bit.
So measurement is quite complex. It is quite recent. We also heard in the morning the AFM, someone was the first user of the AFM. So it's not a trivial thing, but a lot of nanotechnology has developed empirically. DuPont has been making TiO2 for ages now. And I still recall my first project studying TiO2 fabrication. They wouldn't share anything, but they had their engineers on staff who really knew it empirically. They knew if they turned this valve, this is what would happen. And these are reactors where you're producing tons per hour. Obviously, instrumentation and measurement will aid that, and much of it is happening now or beginning to happen. And even in one of their reactors, which is turbulent and such a large scale, it's not an easy thing. So they have empirical knowledge, and some developments are indeed empirical. You twist and turn things and get something, it works, right? And you make your millions.
Ladies and gentlemen, I hate to cut off discussion, but we have to move on to the next cluster. Let's thank the panel for very stimulating discussion.